Maybe didn't start the recording there. Sorry about that. All right, so we got the maximum that is down below the minimum, max minimum. Now we need this one. How do you want to get it? Yeah, so maybe section it might be easier other than doing all, you could do all these areas. They're both going to be a little challenging. The beam, so I'm going to draw a little beam here. How long is this beam? It is 8 plus 4, right? So this is 8, this is 4, and then this X is 133, right? So 12, 13, 3, 3, repeat, all right? So this is 13, 3, 3, repeat, feet. And then, oh geez, put that dimension in the wrong spot because I need AY in here at 8 feet. So I'm gonna plop that in there. So this is 8 feet. This is the overall distance. And we're 23.33, right? And we have a distribution on there, 1 kip per foot. So, yeah, we're 13.33 for overall, right? But absolutely, we have to redo it. Yeah, I mean it's 1 kip per foot, but we have to recalculate it for sure. Does the 10 show up? Yeah, because our cut's right here. So now we also have the 10, right? And that's how far from here? Yep, 1.33 feet. So it's not complicated. It's a little complicated. I might need a better picture, I think. So I'm going to draw a better beam that's a little larger so we can work it. It's my distribution. I know my overall is 13.33 feet. I know there's this one, 10 kips at 1.33 feet. And then I have the 23.33 kips at 8 feet. I think that's everything. 1 kip per foot, right? And what we want to know is the moment here. We do. Yeah, I drew it distributed, but when we do this moment, we definitely have to concentrate it for sure. So moment, I'll just call it max. It's going to equal, and I'm just going to write them out. It's going to be 10 kips times 1.33 feet. And that looks like it's a counterclockwise motion moment. So that's positive. And then we have 23, and I think it's 4 feet between, right? 4 feet between here and here. So we have the 23.33 K times 4 plus 1.33. So 4 plus 1 is 5.33 feet. do that right? Okay, and that is rotating. Yep, so that's negative. And then the only thing left is the distribution. So that distribution is, we have to concentrate it first. So it's 1 times 13.33. So I can just write that 3.33 K, because the feet cross out when I multiply those two times each other. I'm just left with K's. And now I need to multiply by the lever arm. Yep, and I'd probably just write it 13.33 repeat divided by 2, which is what you just said. And that rotation is, yep. And all that is equal to the maximum moment. Yeah, I don't know. Maybe the areas would have been easier. I don't know about that, because there was a few areas to do. So the double check obviously is to do it both ways. Soon as somebody confirms that, I'm happy. Yeah, positive or negative? That's what I get. Well, I'm just going to write it as 1.5. And it's not kip per feet, it's a kip feet, right? It's a moment. Yeah. So that's a mistake that gets made a lot, is people get confused with the distribution and a moment unit. Moment is kip feet. So 22.15 is this one. And does come out, yours come out negative or positive? It means it didn't cross. Yeah. So I assumed it crossed. Yeah, so I drew it over there. So didn't do that. Don't know if I like that. I don't believe that. It's got to cross. All right. Why are we getting a negative? Oh, it's opposite. Remember? We calculate, what did we do? We calculated the beam moment. We calculated the moment out here and we get negative 22.15. That means that this thing is going this way out here in the negative direction, correct? And we always resist it with M max. Yeah, so that means that M max has to be a positive 22.15 kip feet. Ah, good. Excellent. That makes sense? Because when we did these moments, we looked at everything going on out here to figure out what the effect is out here, and then we resist it with the internal moment. So the sign changes. All right, so all of that, just so we know the maximum moment, and the maximum moment is the absolute value on the graph. So if you were doing bending stress, all that work to find out that it's not the max, actually, that's the max, 32. So there's only one way you know those, by figuring it out. So when we go to bending stress, we want to use the biggest number on the graph. Yeah. Nothing, because there's no next diagram. Just shear moment diagrams, all we have. So when it crosses, that just means that's the point, like that's the inflection point. Would that be, yeah, that would be the inflection point. up here that would be from this way to this way, right? Where the concavity changes. Yep. Good, super good. Which is fairly important for deflection, so, but we'll get there when we do that. Questions? Yeah, if you got them done, deliver them. Nick is getting rid, he wants to get rid of that, I can tell. Oh, done with that. Yeah. You want to keep it with you? Turn it in later? Yeah, I'm okay with that. Okay. Right. That works. All right, I want to do another one before we're out of here. Actually, I just want to look at your homework because your homework's challenging. I gave you homework before the exam, so I'd like to at least look at it a little bit before we go off and try to do it. It's just more of a shear moment diagram. So it's out of the bending stress chapter though. So the bending stress part, no, it will not be on the text. But we're pretty close to just being able to do bending stress because once you get the moment, then it's just C&I is all that you're missing. So bending stress is our end goal. And they actually use this F sub B for bending stress, so I'll start using that. And that's MC over I. And M is what we just found out. That long process was just to get the maximum moment. So all this work, right, just to get the 32, which then plugs in here. So C and I, that's pretty straightforward. If I had a L shape, then I would just look up where the neutral axis is and choose the largest C value. So there's usually a couple C values if the shape's not symmetrical, right? You want to use the largest C value that you can find. And then I is the inertia. Again, we look that up if it's a structural steel shape. So those two, pretty easy to get. It's the M that's the pain. Where's that maximum moment? How much is it? That's what we need before we can go for bending stress. So the next chapter is stresses and beams. And it really is just what we did and then learning to run this bending stress equation. There is another stress called shear, but we'll do that after the exam. So the one you're going to do is number 3. And number 3 says W18 by 71 steel beam supports a superimposed uniformly distributed load as shown. So they do show it to you right here. So simple beam, right? Superimposed uniformly distributed load. Now, when you're dealing with structural steel shapes, sometimes it'll say include the weight of the beam. Sometimes it'll say neglect the weight of the beam. You know, that's kind of the designer's choice. This one says be sure to include the beam weight. So when you're given an 1871, the first number is the approximate height of the beam. They refer to it as depth, but it's just really how tall it is, right? And then the second number is pounds per foot of the beam. So for every foot, this beam weighs 71 pounds. And they're saying, you better include that. This is a heavy beam. And you're calculating bending stress. That beam is stressed just due to its weight, right? That's why we include the 71. So this one says, hey, you got a beam with a 400 pounds per foot distribution on it, and then another 71. So really, you just write 471 for your distribution and go after it. Okay. If it says neglect the weight of the beam, then you just don't worry about it. That means there's enough factor of safety on this project that we can just neglect the weight of the beam. Not always going to happen with W shapes, because there's a lot of weight in W shapes. But like wood timber beams, you know, their weight, it might be a couple hundred pounds, but it's carrying 40,000 pounds. Like, you know, we'll just neglect the weight of the beam type of thing. Height. Yeah. So a W shape is what common folk call an I-beam. They're not I-beams, they're W-beams because they have a wide flange. That's where the W comes from. The flange is wide. True I-beams, and there are I-beams out there, look more like this in perspective, like the flange is very narrow. I-beam, W shape, much wider, same height kind of thing. Okay, so if they call out a W 18 by 71, the 71 is 71 pounds per foot. And the 18 is just the call out for what they call depth. I kind of call it the height of the beam, but they refer to it as D depth in the back of the book. And we always want to look that up because it's rarely actually 18, right? So let's see what an 18 is just for fun. I can find the W shapes. 1871, the height of it is 18.5. So that gives me C right away, because this thing is symmetrical. C value, 9.25, right? It's a structural shape, so I can look up the I value, 1871, IX, 1170. So those two are done. C's done, I's done. I just need the moment. So that's where most of the work of the problem comes in. It was a distribution, simply supported, no side load, right? I think the distribution is 471 pounds per foot. What's the span? This is what, number 3? Just giving you a little bump start on this. 28 feet, holy smokes. 28 feet's a long ways. That's a big span and a big load. How much is AY and AX? Yeah. Oh, good question. Because I'm rushing. Because our time is up. Yeah, so it's 28 times 471 to get the whole load, and then half goes each side because we see symmetry. It looks like 6594. pounds on each side. You all can draw the shear diagram and the moment diagram. All right. Goes up, comes down at some slope, and goes up. And again, since we see symmetry in the load, we're going to see symmetry in the shear curve. We're going to see symmetry in the moment curve. So I know the moment is maximized here. I think about the deflection. Looks like the moment is positive the whole way. So we're going to be up above with a max here. Straight line slope gives me a curve. Second degree parabola, M max. Once you have it, put all the pieces together, you get the bending stress. That's a big portion of what we have left to do, is to kind of practice that a bunch. And then we'll add the deflection in and we'll have pretty much everything we need. Bending stress, we'll do a shear stress, and then we'll do deflection. But for the test, just the diagrams. Simple ones to hard. Yep. You can get a triangle load. Yep. Yep, let's do it. All right, so we have a snow load. That's what gives us these kind of loads, typically. Snow drift. You can simplify them by a triangle. I'll say it's 400 pounds per foot. And the way the load curve works is it goes from 400 pounds per foot down to 0, nothing at this end. And we will simply support it, because we're not going to go away from that. We could cantilever this, but it's all right. We'll just do something like that, right? And we'll say it's 10 feet. So we don't have to work through the numbers. We should be able to just draw the shear curve. We still just follow the forces. We're going to stay exactly with that concept, right? So right here, it's 0. Actually, it comes up, whatever this is. So that's going to come up some, right? It's probably bigger here, I'm guessing. Looks like there's more downforce over here. So this is a bigger number than this. If I wanted to know exactly what's going on, I'd have to calculate, right? But then what happens is we start down at some curve, because we know the progression is from straight line slope, it's a curve. And its second degree parabola is the first one. If we had a parabolic curve, then it would be third degree, fourth degree, right? Because that's the progression. So I know it's going to be a curve. It wants to come down. So I got to bring it down. And then I know it's got to return back to here. So this does have to come over and down and then return. This value is that. This value is that. And then this does this. Okay. Yeah, so where it crosses, good question. Like, how could we figure that out? Like, where is this crossing? Huh? Yeah, parabolic areas are in the book. Yep. Yeah, so you can calculate this parabola, and then you can calculate this parabola and determine this value x. Same kind of thing, ratios. That's bending stress. Yep. Use absolute value. Don't put the negative in. Yeah, absolute value off the graph. Yep. Yeah, so what's the moment going to look like? We know where this crosses, it's at a max. What's the whole beam look like? Deflection wise. Maybe like that. So we're looking at a positive, right? We know the slope goes up, plus, and over here it's negative. Okay. And we also know that if this is second degree, then this is going to be third degree down here. And in the book, you'll see where it says third degree parabola, second degree parabola, so you can calculate areas if you really want to. But it's going to start plus pretty steep. It's going to zero here. It's going to look a lot like what you've drawn before, but it needs to be noted that it's third degree. So if somebody wanted to calculate areas, they could do that. This max lines up with the zero location in the shear. Okay. So there's a couple ways to identify this location. That's the tricky part, right? Because we need to know where this is. Then we can just take the moment at that spot and we got it. Okay. So it's going to be helpful if we get these numbers. So I'm going to get that. We have to concentrate our distribution through the triangle. That's 1/3 the base is where it gets concentrated. So 10/3 right here. So we need the area of the triangle. One half the base is 5 times 400. 2000 is the value of the concentration. Oh, geez. Thank you. Right, because that's how we concentrate distributions. We find their area. I just did 1/2 the base times the height. And then I just know it's 1/3 from this way, or it's 2/3 from this way. The location of that concentration. So then I can do my moment. Moment about A gives me BY, or a moment about B gives me AY, either way. So I'll do the moment at A, right up here. Give me 2000 times 2/3 of 10. What is that? Yep. So that's that moment. And then I'll put in my unknown BY times 10. So I'm doing my moment at A here. So BY times 10. That rotation is positive. This one's negative. Set it equal to 0. BY equals. (13.3) repeat. So there's 1,333 here at BY. So here, there's 2,000 coming down. I just take the difference between those two to get that 666. You got a total of 2,000 coming down, right? Complete total. So if we find 1,300 here, this one has to balance. These two have to add to that one. Yep. So to figure out like where this point is, now we know that this value is 666.66 K, and we know this value is 13 point, oh geez. Actually, it's pounds. And we just have to figure out like where it goes from, you know, one location, where it goes from positive to negative, really, right? So how can we do that? Yep. So it's not where the 2,000 is. It's where this area and this area are equal. Like where's the halfway point, right? So it could be where the 2,000 is. Probably more than one. Yeah, yeah, it would be 2/3 and 1/3 for sure. Yeah. So I drew it graphically not correct. But it would have to be where that centroid is. You can also just say, okay, well, if I have 666 going up and 1333 going up over here, 2,000 coming down, where does all that balance out? You're like, where would the moment be equal to 0, right? And that'll give you that location. Good question. Gets tough though, doesn't it? With that kind of a curve in the load, creating that kind of a curve in the shear, creating that kind of a curve. You just have to continue to follow your rules. Hey, the moment is positive, it's got to start up, and it's negative over here, it's got to come down, right? So that gives you the basic shape of the curve, and then it's just mathematics to figure out this max. That'd be the really hard one. Yeah, we haven't done any of those. I'm not going to give you a triangular distribution. I'll probably give you a rectangular distribution that could change in height. So a couple distributions, something like that. As the hard one. You'll see a couple pretty straightforward ones. Knock those out and then think about the next ones. All right. We are done. Yep.